Gentlemen from Tiqit.
Berg.
Berg and Blasch.
Well, thanks, Yuri. It's a pleasure to be addressing you guys again. I talked to you back in '95 on the Pentium bug and also on shoe spaces. Those are the days when the Pentium was having a bit of a struggle with hardware that I think we haven't seen since. So I want to talk today, along with actually Ian and Henry are going to do most of the talking. I'll just give a quick intro here and try to give a little historical perspective on how this particular project came to pass. The project itself is the development of a little handheld computer that is obviously bigger than a PDA, also obviously smaller than a laptop. It's a x86 handheld running all the same things that your laptop runs, complete with keyboard and PCMCIA, and Ian and Henry will have a lot more to say about that. I want to talk about the background that led up to this and some of the work that's going on at Stanford in parallel with the Tiqit work that's in support of handheld computing of this kind. So the Stanford Wearable Computing Laboratory was set up in 1998 with the vision of having a truly mobile full PC. And by truly mobile, I mean not simply mobile in the sense that a laptop is mobile, where you can carry it wherever you want, sit down and type on it, but even more mobile than that, where having carried it to some point, you might want to keep walking, but type or use it on the go. So you're looking for what we think of here as true mobility. So now, when it started, the going-in premise was x86 architecture, and this was in the face of other people in the wearable community saying, oh, we want strong arm because that's where the really light-powered processes are. And in fact, that's been a popular point of view, but there is this counter-argument to the power issue, which is, well, okay, but you give up software compatibility with PC platforms. And so the benefits of sticking to x86, the enormous body of software, all that shrink-wrap software that you can get at Circuit City or wherever you buy your software, and it's a platform where so many people are familiar with it that you can easily hire people familiar with it, and the pricing and the availability of parts for machines that you're constructing on it are very much controlled by commodity pricing. It's a commodity space, and by commodity space that covers both things like the supply chain and the pricing of everything. So the first project we built was the Matchbox web server, which was a kind of a lightweight project in terms of not involving much effort. It was a 1 cubic inch Linux-based server. And that made it into the last 3 editions of Guinness Record, where it's steadily maintained the record as the world's smallest web server. There have been smaller machines as candidates, but it's the only one that stayed online. And so I guess whenever Guinness looks up the other ones, they never find them online, and so we're always online. So, yeah. So it was also the basis for JumpTech's DIM PC advertising. JumpTech is the company that actually made the key module in the center of the machine, and within a month, JumpTech had sort of latched onto the fact that this was drawing some attention and used it as the basis of their advertising at CeBIT for their booth. They had this giant screen saying, "Die kleinste web server der Welt," the smallest web server in the world. They're very proud that their DIM PC was being used that way. So after that, we built the Matchbox PC, which was an expansion of this to include VGA, Ethernet, and a 340 megabyte disk drive based on the IBM microdrive. And that, by the time that this got recognized by the Computer World Honors Symposium, I guess this was Tiqit had started. It was a finalist last year in the manufacturing division of Computer World Honors Symposium. The other finalists were Boeing, Dell, Delphi Automotive, and NTT Docomo. NTT Docomo won for their iMode telephone system. Delphi was in there. Delphi Automotive was in there for the OnStar system, and oddly enough, Tiqit was in there too, along with the other 4 players. So we were actually very proud to be the only tiny company in the manufacturing section. Now, the shortcomings of the Matchbox PC are, in a nutshell, that it's feeble and uncivilized. It's feeble in the sense that it's a 66 megahertz machine, well, these days 133 megahertz, 16 meg of RAM in those days, now 32, hopefully 64. It's uncivilized in that there's no display, no enclosure, all sorts of, no PCMCA, no keyboard, all sorts of things are missing that really are required to make a civilized machine. So the extension of the vision then from just the original vision of the truly mobile PC is to overcome these shortcomings that you encounter when you just try to do something the easy way, and the Vision Plus is that those shortcomings can be overcome. Well, now the question arises, is there any point in pushing on with this? And this is, in fact, the big thing that we continue to agonize over every day. Is this vision commercially viable? So 2 years ago, it was simply almost an academic question. Maybe you just go and build them anyway. What's the point? And then you have to say, well, maybe there is no point. So we formed a company for the express purpose of finding out whether this vision was commercially viable. And if it was, then, of course, you make tons of money, which was always part of that vision. But so there's more to it than merely an academic question here. So the requirements are, well, there's a list of them. You can read them for yourself. And if you were to have to make up your own list of what are the requirements to pull off such a project, hopefully you'd come up with a similar list. You need a talented and committed team. You need a good balance of engineering and business skills. You need a vision of how the user space is going to be organized, and although the vision ought to be clear, it also has to be flexible because that space changes from one year to the next, and it also changes in the perception of people. So both the perception of the vision and the actuality of the space keeps changing. You need resources, and most of all, you need tons and tons of luck. In such an enterprise, lots of luck. So an additional feature of this particular project is that it's maintaining a working relationship with a local university, which is, I think, if you were to look at Sun Microsystems 20 years ago, which was a Sun spin-off that I was involved in, it met the requirements there, but didn't maintain a working relationship with a local university, which might have been good and might have been bad, but I think it's a good thing to be able to do that, and I'll argue why in a moment. So here we achieve that by maintaining the lab's research focus and at the same time as Tiqit pushes on with the question of commercial viability. So I'll say a little bit about what's happening at Stanford in parallel, and then pass off to Henry, and he'll tell you about what's going on at Tiqit. So there's two areas. The first is wireless for handheld computing, with one PhD student, Majid Amami, who's looking into mobile antenna design. And I actually was lucky enough to talk to Jim Kajia this afternoon for an hour. And Jim knows an incredible amount about antenna design for somebody who's supposedly on the graphic side of things. So the two things we're doing is, first of all, to pass Maxwell's equation solver. And the trick in this that differentiates it from other equation solvers is that the constraints are all locally propagated. And the way that's done is by noticing that Maxwell's equations are relativistically invariant. So that lets you speed things up. And it's independent of whether you think your program should be working in the time domain or the frequency domain. So if you're all computer scientists here, this is all going to be sounding horribly like EE. But hopefully there's a few EEs here, and this should be familiar stuff. So the other thing then is we're looking at multiple antennas talking to multiple transmitting antennas talking to multiple receiving antennas, where the receiving antennas are distributed all around the handheld in suitable places. And we're trying to use this simulator to figure out how to optimize the locations on both sides. And the goal here is to use scattering reflected signals to give you a very broad propagation path, so that it's so broad that any one obstacle will not kill the whole path. And so you get a kind of a holographic effect that renders it immune to local transient disturbances. The other project is speech for handheld computing. Kevan Mahaja and Ramon Prieto working on that. The thing that we're focused on is at the front end of speech systems. We figured that the back end has received more than the lion's share of attention in speech systems so far, and so now we're trying to return the attention to the front end, which has been awfully neglected. And we're very focused on the glottal cycle, which strikes us as being as the Achilles heel of most existing front ends. which emphasize the frequency domain. So the advantage of emphasizing the frequency domain, well, one of the advantages is the ability to tune out noise. But that's a benefit that's neutralized by the effect of glottal closure, which has a resynchronizing effect every 10 milliseconds of shifting phase, and so messing up your Fourier transform unless your Fourier transform is careful to look at it. And as a result, it creates its own noise added to all the other noise in the system. And in order to get better recognition, you'd like to reduce every source of noise, and that's one of them. So we have a technique that we call rapid response resonance analysis that gives us a way of tracking frequency variations more quickly than one might think reasonable, and in fact it is impossible with Fourier transform, but it's possible. It's quite doable here. So the last thing then is the fact that we can't do this without calibrating the front end. We can't just simply fiddle with the front end hoping that it'll be better. You have to have some idea of what you're aiming for. And so this actually involves a fairly carefully tuned back end that has to be stable in order to judge the front end. You can't have you can't judge tuning a front end if you're tuning the back end at the same time. And the results aren't very useful if the back end is in a half-finished state where you're planning to change it anyway. So you need the back end to be in excellent shape before you can really judge the effect of fixing the front end. So this ends up chewing up more time than one would think was reasonable in such a system. So that's all I have to say, and I'll hand over the floor to Henry. Oh, it's a hidden Markov toolkit, and the thank you to Microsoft was thank you, Microsoft, for making that source public again after buying it. So bought it, and then you sold it, and you released it again. So we've been able to look inside it and take good advantage of it. Yeah, that's right. Yeah.
Okay, my name's Henry Berg. I'm going to give you a brief overview of sort of the design process that went into the handheld that we brought with us today. And then afterwards, feel free to come up, and we brought several that people can look at or play with. So the overall challenge for us as a design team was how do you design a fully functional general-purpose handheld computer as opposed to the handheld computers we're more used to seeing nowadays, which are sort of application-focused for very specific needs. So just to start, why did we want to do this? And the main reason was that in many cases, mobile applications really aren't served very well by existing products. They either are specific personal information management type applications where they're well served, but the general purpose existing software is not served at all. So people in these applications, they either pull out a laptop, which is awkward and ungainly, or they use no computer at all and go back and enter the data into their system later. So there's no handheld solution that allows people to leverage their existing software, and that's what we were trying to solve. For many applications, if it's done right, you can replace sort of what people were kludging with their laptops. So I just wanted to overview, from our point of view, the sort of existing categories and what is good and what is bad about them. So they fall into PDAs, laptops, web pads and tablets, and special purpose computers. So PDAs we're all familiar with. They're excellent for the set of tasks that they were designed for. They're small, lightweight. They have very low hardware costs. They last for a long time, assuming you don't actually do anything like transmit on a wireless or do something they're not designed to do. And they wake up right away. But because they use processors which are specified for mobile environments, they really are very limited from a computer point of view, which means the applications are limited, your existing software is incompatible. Often, even though the slots or the connectors might be compatible, the actual expansion hardware has to be specifically supported by the handheld. The only alternative, if you want, and what's happening now in industry is where people want to use handheld computers to solve a problem, is to undertake a very large and very expensive porting effort. So you see a lot of companies spending a lot of money to port their specific software applications to Pocket PC or Palm OS. So sometimes this works, other times it's a disaster, and our goal was to provide a handheld that circumvented this process entirely. Laptops we're all familiar with. They basically let you carry a computer everywhere, leverage all your existing software and operating systems, but they're large, they're heavy. You have to sit down and unfold it to use it. You can't walk around unless, I mean, you can try, but it doesn't work very well. And that really sort of imposes a barrier between the user and the computer, and between people who want to bring a computer into a situation and the things they're interacting with. Web pads and tablets, well, the industry has been spending billions of dollars on them, but they have certain problems and certain advantages. The OS is usually completely compatible, so that works fine, and the screen's big. But in many cases, the existing applications people want to run really require a keyboard and a mouse. So trying to work on a tablet and a pen-only interface, while that can work, and in many cases you can customize software to work that way, it really breaks a lot of applications that people want to use. The other thing that we're up against is special purpose industrial computers. I just picked a few here. There's a whole bunch more. And those are usually designed to solve a specific problem in industry for a vertical market. So they work very well for what they're designed for, but they tend to cost a lot. They're really inflexible, and you can't use existing software that people are running on their laptops and desktops to solve these problems already. So this chart is basically, on the y-axis, we plotted mobility of various computing applications. On the x-axis, computing power. So the PDAs are great on mobility, but they're extremely bad in computing power. They really break down if you try and do any kind of RSA computation or real computing on them. On the other hand, in this circle on the bottom right there, we've got existing portable and tablet PCs. So that includes laptops and tablet PCs and web pads, where they often are great on computing power, but they're not super mobile. You can carry them around, but they often require two hands, and you have a lot of the same disadvantages as laptops. So the reason we started this effort is that we felt there was this huge gap in between, where what you really want to do is provide the mobility that PDAs provide, but move over on the computing power, which is just not addressed in the marketplace right now. So as a start to the process, we asked ourselves, what are the general requirements of such a PC? What does it mean to say we want to design a general purpose handheld computer? So we outlined them sort of at the basics is this. So you want to support operating systems that people use now, which means operating systems like Windows XP, like Linux. You want to support the operating systems that people are already deploying. As part of that, you want it to be compatible with the existing applications that people want to run. So that they can take the applications that are running already and bring them out into the handheld space. So as part of that, you want this computer, whatever it is, to be comfortable and usable, and obviously it's not going to be perfect. You have to compromise on all of these. But you want to be able to hold it and use it and with your existing applications despite the small size of the computer. You want to be able to use existing peripherals and expansion hardware that you're using already in your other machines. And you want battery life that's at least equivalent to what people expect from a laptop. So going in with that set of general requirements, we translated that to a set of technical requirements. So we wanted an x86 compatible processor. We wanted to run at least 300 megahertz. We want at least 128 megabytes of RAM available to the operating system. We wanted at least 5 gigabytes of hard disk space. A VGA or better screen in landscape mode, as opposed to portrait mode and quarter VGA that we expect in PDAs. We wanted a keyboard, because most existing applications require a keyboard. We wanted to be able to control the cursor. Another thing that's often missed is that if you're going to use applications that people are used to using with a mouse or to control the cursor and click on things, you need to be able to control the cursor and click on things. We wanted standard connectivity, and I'll get into what that means, but we wanted what people expect their computers to be able to connect to still be possible with our machine. And last, we wanted a laptop class lithium-ion battery. So here's some of the things that standard connectivity implies. So the ones in red were the ones we ended up with, but we kind of divided them into 6 categories. And anytime you design a computer, you have to try and address each category separately. So on the top there, in order to connect to cell phones and existing data communication devices, we wanted to provide a serial port. It's probably the most legacy that we have. We provided a USB connection. IRDA because people expect portable machines to have IRDA, the full spectrum of audio connections, a basic video connection to output to projectors or monitors, and then what we felt was really important was we wanted to provide an utterly standard way of expanding the device. So instead of putting in a customized expansion slot or something that would only work with particular things, we wanted something that would support the full spectrum of what industry is already making available for laptops. So we went with a card bus Type 2 slot. And lastly, because we wanted to be able to interact with all sorts of other portable devices, we wanted some kind of flash memory solution. So there are several in the industry out there. We picked Secure Digital because we feel it's a great size and it's likely to go places. It's also very small. So I brought a card if you aren't familiar with it. So here's our target specification for the computer. And I listed up here, these are the sort of WinXP recommended requirements. So our goal was to come in at something that could comfortably run Windows XP, but also recognize that we're a handheld computer. We're not trying to be a desktop. So we spec'd it out at a 300 megahertz processor, 256 megabytes of RAM, which is more than we needed, mainly because we need to allow for the CPU in the case of a transmeta, or for the video in the case of the national CPU to steal some of that RAM. We used a Toshiba 5 or 10 gigabyte hard drive, 10 gigs, and the ones we'll show you today. A standard headphone jack, a standard cell phone earbud microphone jack, a card bus slot, a USB connector, power connector, Secure Digital, IRDA, and then a high-density docking connector for everything that you need for a single-point connection to connect to your environment. This might include a monitor, a keyboard, a mouse, speakers, a microphone. It would depend on the application. So what are some of the trade-offs involved in a design like this? One of the big ones is the smaller you make your PC board, the more expensive it is to produce. Anytime you try and compress a PC board down, the number of traces goes up, the trace widths go down, the size of the vias goes down, number of layers goes up, so the board becomes a lot more expensive. So in the size that you figure out you want to do, you want to make the biggest board that you can possibly fit. PCB part size versus availability and cost. It'd be great to take the leading edge available components. There's all sorts of micro SMD and bump packages out there, which would let you produce a really small board. But if you go and use the parts that are most recently available from all the manufacturers, you have something you'll never be able to build because somebody will have a production problem, or they'll only be able to get you 5, or they'll charge you an absolute fortune. So the goal is to go to the most advanced package they offer and then take a step back to the most advanced package they offer that's actually available at a reasonable price. The usual ones of processing power versus the size of the unit, how hot it gets, how long the battery lasts. You want to try and find a sweet spot between offering enough power to let people do what they need to do with their computers, but not offering so much that you end up with a computer that's too big, gets too hot, and flies through its batteries. The overall size versus feature set, if you look on the back of a large regular laptop, there's about 80 connectors on there. Well, it'd be great to build a handheld computer that had all those connectors, but suddenly you're going to balloon up. So we have to pick a properly optimized set. And lastly, like we talked about before, are you building something that's supposed to be a general purpose unit, or are you building something that's specified for a particular vertical market application? So our goal was to build a general purpose computer, so we didn't want to make any decisions that were only used in the oil industry or that would only apply to the healthcare customer. So some of the engineering challenges we faced. Trying to fit all this in mechanically was very, very difficult, because you have all these pieces that have to fit in sort of like a three-dimensional jigsaw puzzle, and changing one piece would often cause a lot of friction with all the other pieces. So that you read a lot in the trade press about sort of the pressure between the mechanical engineer and the electrical engineer, and I would say that process is almost violent in that the electrical person, which was me in this case, would say, well, I need this, and the mechanical person, who was Ian sitting over here, would say, well, you can't have that, and we get into huge fights over a millimeter. And you read very similar things in like product design press about the Kyocera smartphone and things like that. Heat. Well, that's a big problem. In a lot of PCs, you have to use fans. They use various kind of heat pipes, various kinds of crazy heat sinks. And trying to deal with heat without blowing up the size or getting too hot to hold, and you see a lot of bad press about laptops that get too hot to put on your lap. Well, In a handheld, it's even worse, because now not only is it in your lap, but it's in contact with bare skin. So we'd had to do a lot of work to try and dissipate the heat. We wanted very much not to have a fan. So we have no moving parts other than the hard drive in the device. And we ended up having to really sort of invent some new ways of dissipating and moving that heat around in such a way that we don't burn people's hands, but we can also run at the full speed of the processor. Assembly. This one's really easy to overlook, especially when you come at it from an academic point of view. You can put something together, and in fact, we designed an early prototype of this machine that it may work wonderfully, but if you can't assemble it in volume, it's not going to go anywhere as a product. Because as soon as somebody starts doing their due diligence and studying how are we going to actually make this, and then it turns out that it takes somebody an hour and a half working with a little screwdriver to fit the parts together, you're dead in the water. So we spent a lot of time optimizing for that. And lastly, we put in a force-sensitive joystick, which, as far as we know, has never been used on a handheld, but everyone's familiar with it on their laptops, the little nubbin thing. So we integrated that in, which took a lot of work itself. Some of the things I mentioned before, motherboard density, a big challenge. When we first spec'd this out, we said, okay, well, what happens if we use a standard CPU and we just try and compress everything down? And it doesn't work. You end up with something the size of a laptop because standard CPUs and chipsets are basically designed to support nothing smaller than a laptop. So we had to sort of go outside of the standard expectations there and look at what CPUs and chipset type products are available, even if they're not meant for handhelds, that would work in a handheld. And that's how we ended up with the Geode processor that we used. We wanted to use very dense packages, but avoid pre-production or otherwise expensive parts. And again, the tension between mechanical and electrical, trying to design a computer motherboard where you have to worry about mechanical integration in a device you're trying to get as thin as possible, means that in many cases you've got enormously complicated geographic maps of nothing's allowed to go over 1.8 millimeters here, nothing's allowed to go over 2 millimeters here, and that just makes the whole design of the circuit board process a nightmare. A big one, the power supply. Well, one of the things about making a general purpose handheld computer is you don't have these handy custom designed chipsets that are designed for handhelds that don't need a lot of voltages. You're trying to provide a complete computer. You need, in this case, 5 switching power supplies, which means you have to put 5 switching power supplies, but also take every manual for every chip for the switching power supply and throw it out the window. Because everyone will say, well, you leave this much space around it and don't put anything this close to the inductor. And all of that goes right out the window because you just can't do it. So we had to build a board that would integrate all these switching power supplies, but where the interference between them wouldn't completely demolish the functionality of the unit. And that was a big challenge. And then just routing and producing the board meant that it was very hard to fit in all of the pieces that we needed, and it was very hard to actually get a board layout that was possible to fabricate. Oops, so here's what we ended up with. And you'll see this. You can come up and look after the talk. So the force-sensitive mouse stick is on the left there, the blue. On the right, we took the 2 green buttons, are the left and right mouse buttons. The right keys on the far right are the cursor control keys. And the idea was to support a mode where you type with your thumbs on a keyboard, but then shift your thumbs up to control the joystick and the mouse buttons. Then we also wanted to be able to shift to the usual handheld mode where you hold it in your left or right hands and interact with a stylus. So it has a touch screen. The resolution in this space, the highest we could get was 640 by 480, which was perfect because that's just what you need in order for Windows to run properly. Here's how the layout of the ports worked out. We ended up with headphone and earbud jacks like I talked about, the secure digital slot on the left. And then along the top of the unit, USB, IRDA, power, the docking connector, and then the giant card bus slot, which looks a lot larger when you see it on a handheld than what it looks on a laptop. So why is this a good solution? What makes this an interesting product? Well, the basic idea is that enterprises are able to now deploy handhelds running their existing software packages. they can then use the full line of wireless solutions, which are already available to support laptops, and you can customize that for each region you're in. So one customer may like an 802.11 card, but another one might want a GSM cell modem. So by only supporting the PC card slot and not integrating any of these solutions, we don't make that choice for the customer. For the first time, on a handheld at least, you have the CPU and disk space to allow for local processing. So a lot of companies are specializing right now in developing middleware for handhelds, where they take the existing enterprise data and they massage it, and then they hand it out over some kind of connection to a handheld. Well, that works great as long as you have wireless connectivity. What happens when you lose wireless connectivity, which, as everyone here knows, in the United States at least, you can do just by driving for a couple miles. So what do you do that, or to work around that? And previously there was nothing you could do. Now we offer a solution with the disk space and the processing power to actually run local software and put the whole database, or most of it, on your handheld unit. Security is a big one. Existing public key infrastructure and VPN-type software often breaks handheld computers. So we met with several people who, in one case, they just deployed Pocket PCs through an entire section of the company, and then they upgraded the security requirements, and the software wasn't available, and the hardware couldn't hack it, and suddenly they were cut off on all their Pocket PC devices. So by offering a standard PC, but in a handheld, all of those things work because they were designed to work on PCs. Our goal is to lower the total cost of ownership of a computer for the enterprise by allowing them to share all of the software, training, and support infrastructure with other PCs that they're already deploying. On another tack, it's also a mobile thin client. So thin clients are a fairly new product as far as enterprise consumers are concerned. And it's sort of a throwback to the 70s as far as computer scientists are concerned. But you see products like the compact Evo T20 is what the photos of, where they're designed to boot up and run Windows Terminal Server, or Windows Terminal Client for Terminal Server. And organizations deploy them in such a way that they can keep people from running MP3 files and using floppies, and in that way it's kind of an evil machine. But organizations like it for those reasons. So one of the things we did was, all right, we didn't build something that's a desktop computer that's going to run a 1.7 gigahertz machine, but we built an exact equivalent of a high-end thin client. Now, it's not only a thin client, though, it's a thin client that's now mobile. So one of the things we let people do is, if you're going to deploy thin clients, and everyone's got one on their desk, well, if you have some of your workforce that needs to be mobile, you can give them an 83 instead, and now they have a mobile thin client. And that's one reason why the single-point connection that I showed you in the picture before was designed to allow you to connect to a full-size monitor, keyboard, mouse, the network, and everything else, so that you can dock it in, work as a thin client, and undock and be mobile. I did want to talk about some of the other products that you probably are familiar with, but that have been in the press recently. So one thing that you have to start confronting when you start building small computers is these new transportable cores. So on the right is a picture of the iMod from a company called Aquis. It's been around for a couple years. And on the left is the IBM Metapad that's been recently in the press. They compress it down even further. So the idea here is you have a core that you transport, but the core itself has no user interface or power supply and doesn't have to deal with all the engineering issues that come with it. So you can use this, particularly the new IBM one, to make a handheld. But our view was, if you do that, you end up with something that's bigger and of higher cost and more awkward than a well-designed handheld, because it wasn't designed to be a handheld, and you have to deal with all the modularity and connection issues. The other point that we sort of feel that undermines transportable cores is that, and one problem that Aquis ran into big time, is that if you were saying, use a transportable core as your only machine, dock it at home and you're in one shell, and dock it in the office in another shell, and dock it into a laptop shell to travel with, well, without an industry standard, that sort of locks you into only products from that company. And people are very unwilling to take that kind of risk. Another one that's been in the press a bunch lately is the OQO computer. There's a picture of it here. From our point of view, this is an 83, only take away all of the things that we sort of thought through that allow you to interact with the machine. So their idea is that you take a transportable core, you slap a very minimal user interface on it, and that allows you to interact with your data the basic way that you need to. we feel that that doesn't really give you a portable computer. It gives you a transportable core that has a screen on it. One thing they did do is use a TM5800 instead of the Geode, and then they clock it down to be equivalent to the Geode when it's mobile, but that lets you clock it back up when it's docked. So that's one thing we're evaluating whether we want to do or not. One big problem if you do that is cooling. So just an overview. We're a small computer design company. We're in Redwood City right now. Like Vaughan mentioned, we were founded in March of 2000. I'm the president and handle the electrical side of things, and Ian's the CEO and handles the mechanical side of things. Right now we have 9 employees. We're angel funded. And the picture on the top right there is the Zorro, which was our first prototype of a handheld. We finished that one in August, and now we're sort of at the stage where we have pre-production prototypes of our 83, and we're trying to arrange for mass production. So I thought I'd just open it up at this point to questions for either Ian or myself.
How do you compare it to the compact ITSI?
Well, the ITSI was sort of designed as more of a research product. So, for instance, it has buttons all over it. It also was designed much more for a Unix type of focus on research. So while we looked at that, we were really trying to take a very practical, like, let's not design an interesting research product, let's design what we think would be a usable enterprise product. That's not as interesting from a research point of view, but that's sort of where we went with it.
Well, one good point to bring out is that we focused on a good user interface along with connectivity. And so there's the PC NCAA port, there's the keyboard. Neither of those are on the ITSI. The ITSI sacrificed these things in favor of getting the size way shrunk down. It also sacrificed software compatibility in the interest of reduced power because it's strong arm based.
It is strong arm based. You can get PC cards for it on the daughter card. But you're right, there's no use.
And one thing about using a strong arm is it sort of rules out a lot of the software that we're trying to run.
Were you able to do anything to solve the problem of using this sort of thing, strong light, like sunlight?
We were able to discover how we could do something about that, but right now we weren't able to get a display that wouldn't wash out. So this is a transmissive LCD on the product now, but you can very easily move to reflective or transflective. It would just be a question of having the compelling reason to force the display company to go into production on that. In other words, they exist. It's just we weren't able to get it easily.
Toshiba was working on it, and we thought we had a product roadmap where they were working on a transflective version and a reflective version of the screen, but they weren't able to get it to work well enough, so they didn't turn it out. Samsung now has a 5-inch screen that's transflective, that's color, and there's another vendor that's got VGA, because we're very much constrained to VGA in this form factor. And there's not a lot of people, there hasn't been a market necessarily for this type of screen.
I mean, that's the big problem. Is 640 by 480 and something you can put in landscape mode in a handheld is a tall order for the industry right now. So it's easy if you want a quarter VGA screen because everyone's putting them on their handheld computers. It's tough if, by your very definition of your product, you need at least 640 by 480.
Did you run into usability issues with the fact that traditionally the mouse movement and buttons are controlled with one hand, and on your design you're actually splitting them up among 2 thumbs?
We were worried that we would, but in reality we find that people get used to this very quickly. And what's interesting about it is in the earlier prototypes we had the force-sensitive joystick on the right and the mouse buttons on the left. And what we found to our surprise was that people got used to either solution fairly easily. It just somehow seems intuitive. And I don't know if that's because people are used to thumb typing now after a couple of years, but we really found that it's just not a problem.
Is that for both right-handed and left-handed people?
As far as we've been able to tell, yes.
But it already is a problem with things like the glide pad, where you have to take the thumb off the glide pad, move it to the. You're describing a typical mouse where you get to completely integrate the motion, which is ideal. But all of the other solutions have a similar disconnect here. At least here you're running in parallel, that is, you're sliding at the same time as you're clicking, unlike the glide pad where you have to lift your finger off and then click.
We're moving to the joystick that we're actually using. The company really likes the idea, and they're trying to integrate a click stick so that you actually can integrate right mouse click.
Left mouse click.
Left mouse click, but we're not really sure when that's going to come out and then whether or not it'll work.
We also don't know whether that will be comfortable. So right now, we have found, and after, feel free to come up and play with one of these. You'll find it's fairly intuitive and pretty easy to use. some people pick it up and they start playing with it and they go, I want to click the stick, and they get frustrated. Other people don't seem to care. So it's when we get the click stick, I guess we'll find out whether that's a good thing or whether that just confuses people.
The one thing is every group we present to, there's no agreement on user interface, connectivity. I mean, I'm sure none of you guys can agree on what you like in your own computer, and so now we're trying to put this down into a small platform. The decisions we made didn't immediately surface. These were off of lots of battles and compromise, trying to figure out what the ideal computer would be. There was no manual out there to say this is the ideal handheld PC that runs x86. And we may not have gotten it right, but we had to put a stake in the ground, and we tried to be as flexible as possible to give everyone as much connectivity and try to grab as many types of user interface that were out there. And then let the market sort of determine it and get general feedback from people.
There's one other point there. Because we also have a touchscreen along with the mouse buttons, you have your choice of which you use. And one mode of operation here is that you can be mousing around with the joystick and using the stylus at the same time. For example, you can, well, we actually don't have the software right now, but you can in principle just be mousing the desk around while you pin down, say, a menu onto the screen. And if the desk is in fact sliding with a much larger area than the screen, you can be just holding things in place stationary while you slide large desktops. So there's a lot of opportunity when you have the touchscreen, buttons, and the joystick all combined working together to experiment with novel user interfaces that nobody's ever been able to think of because they didn't have that three-way combination.
That said, our goal was to be as simple as possible so that people can sort of use the device the way they're used to.
Good point.
So, although you can do all sorts of novel and interesting things from a user interface point of view, that you also can do none of the above and just have basic cursor control, which works for people in a way that if you try and slide things around too much, it can confuse them.
We are as vulnerable to the curse of the PC as the PC itself is. Definitely anything we can do to simplify things is going to be very welcomed by most customers.
What price point did you arrive at?
So our goal throughout the entire design process was, our early proof of concept wasn't so subject to this, but the actual production prototype was carefully optimized to get the price down as low as we could. So the real answer to that is it would depend on how it's marketed. It could come in anywhere from slightly above what the high-end PDAs with accessories go for, but definitely way below what laptops go for. So that's a fuzzy answer, but it's fuzzy because pricing is very fuzzy. In that I would think it really would depend on how high the volumes were and exactly what the marketing plan was. Companies like Symbol sell you a $300 PDA for $2,000 because they put a barcode scanner on it. So, and the reason they can do that is because they sell into high price point vertical markets where people care a lot more about support and being able to accomplish the task than they do about the price.
I didn't notice an integrated speaker, and you've got two hookups for earbuds. Is the idea that you can actually get away with no audio on the basic interface?
I'll just add that to the slide. There actually is an integrated speaker. It's very little, but it plays reasonably quality sound. As for low volume music or for audio feedback, it works fine. We didn't put a microphone on because we found that the people who wanted microphones was mostly for voice dictation and voice recognition, as well as voice over IP, and none of those things would work very well without I just started playing music, but none of those things would work very well without a high-quality microphone that was close to your mouth. So we intentionally left the microphone off, and you plug that in through the 2.5 millimeter earbud jack. But we did want a minimal speaker, although it's an engineering asset.
One objective restriction is the small screen. So if you have to say a Word document, does it take perfect vision to read it?
We were very worried when we started this that by compressing things, if you go too far, that you end up with something that people can't read and can't use. And so our nightmare was that you'd have to take a magnifying glass to use it. Well, and I invite everyone to come up and try opening a Word document or whatever. I think what you'll find is that with normal vision or with normal glasses, you can very easily read this screen. You definitely, if you have bad vision, you're not going to be able to read it as easily as a big screen. But we found that because the incredibly high pixel density really gives you very readable fonts in a way that people don't expect at this resolution. So people are used to 640 by 480 popping up on the monitor and being grainy and pixelated. Well, if you look at it on this device, it's basically photographic quality. And because of that, you can have very small fonts and they're still readable. So we're very pleased by that. It's not as easily to read as a big screen, but it's very, very readable.
I mean, we like to compare it to opening up Pocket Excel, and you see an array of 7x7 or 10x10 Excel spreadsheets, which you completely are out of context, and versus being able to see a 20x20 array. That what is the next best alternative that's out there, and how easy is it for the user to use it? So we're not there yet, but we certainly feel we're better as a benchmark than what the current offerings are.
But we were pleased to discover that by increasing the pixel density, you can really jam more information on the page in a way that's still readable. It's not immediately obvious when you start looking at quarter VGA screens where you can't cram any more information on the display because there aren't enough pixels to make that information still readable. But in this case, it really is. You can get it pretty small.
What are the prospects of having larger pixel dimensions in the future? Larger screens, larger in pixel dimensions.
You mean higher resolution?
Well, basically, I suppose, what's the prospect for having an 800 by 600 screen?
Smaller pixels.
So yes, in fact, you could go with, if the industry wanted to produce such a screen, you could easily move in this form factor to 800 by 600. You run into some technical issues having to do with the glass production because the higher the pixel density gets, for instance, transflective screens get much more difficult, just because it's hard to get enough light through the display. So I guess you could move to 800 by 600. I would sort of abstain on voting whether that would be an advantage or not.
There are many dialog boxes that are larger than either 640 or 480 that run into a problem on 640 by 480. That was a question that I had that I was kind of waiting until afterwards just because I came late, but that may be what your question was aimed towards. Even the properties dialog box for the desktop, I think, if you just open it up, it wraps off the screen to the bottom, and it can be difficult to work with some of those dialog boxes in that case. So is your OK button slightly off to the bottom, though?
It's at the bottom of the screen, but it's very
okay.
VGA dongle.
There are other...
Well, you can come up and look at this afterwards. It's very easy to see, but it's we haven't run
It would be very workable. The usage scenarios I've thought of for this thing, 640 by 480 is going to be more than enough.
So, I mean, we were unsure about that until we actually tried it, and we have not run into anything that is unusable or too large to be usable. But it's certainly a concern.
How about website browsing? Because I don't think anybody develops websites for 640 by 480.
With tables especially.
Yeah.
Again, the work we've done, you run into some cases like that, but it really has been fairly easy to get by.
It's not ideal.
It's not ideal.
I mean, you're able to. I mean, we were always looking at ESPN, and yeah, you can move over and scroll and get your links, but.
Let me take this question real quick.
Maybe you're not in your case, but one thing that breaks very, very badly in old VGA is the system recovery CD that some manufacturers have. I tried to recover on a system recovery. My machine went to old VGA, and all the buttons were off screen.
So it's certainly, as Ian said, it's not ideal. You'd love to have a bigger screen or more pixels, but we were pleasantly surprised that we could, for the most part, muddle through almost anything.
One idea, I wonder, if you consider to take whole site of the screen and put buttons in the back.
So that's something like the ITSE that came up earlier, where they really did play with some things like that, where they put buttons on the other side and experiment with that. You can't type on buttons on the back of a screen. I mean, you could. It's physically possible, but people won't, and it wouldn't work. So
we already moved earlier today. Other Microsoft people were playing with it, and we just moved the return key and the P key, and that caused discussion and feedback. So if we move the keyboard to the back, I can imagine the general user would be appalled.
So the direction things are going, people are. The approach OQO takes is the same as similar to the tablet and WebPad approach, which is take this space that you have, the real estate you have, and use it for a touch screen and a screen, and don't waste space on a keyboard. And what we really felt was we're not wasting space on a keyboard, we're providing a keyboard because software requires a keyboard. So.
Two questions for you. One, are you guys planning to write any special software for it, or is it just going to be
Our goal was to write no software for this whatsoever. This was the goal, was that you would take a device, go to the store, buy a shrink-wrap software package or OS, come back, install it on the machine, and you'd be done. That said, that's sort of an impossible goal. to make the machine really work particularly well in each environment, you might want to tweak some things. But we're mainly a hardware design company, and we're focused on providing the solution that people then, if they want to, can write software for.
And my other question is, what happens when you turn it off? Does it go to sleep? Does it hibernate?
So the design spec calls for it to go to sleep. Because it's a Windows machine, you get the basic Windows power management modes, as in shutdown, hibernate, sleep, etc. What we're hoping is that the Microsoft Tablet PC initiative results in some tweaked things like Instant On that we then can take advantage of.
So what is your realistic life of the battery?
One thing you'll find when you come up and actually heft this thing is that it's fairly heavy. It's 1 pound 4 ounces. And part of the reason for that is because we went very high on the battery. And one thing we were frustrated by, and one of the things that we sort of inspired this device was looking at people using iPacks with 2-slot sleeves and putting in storage and cell modems and 802.11 cards, where they ended up with kind of a ridiculous machine that was, the ergonomics were terrible, the economics were terrible, and the battery in some cases lasted 40 minutes. So we put a real laptop class battery in here on purpose because we wanted people to be able to use it as a laptop. So we're getting right now about 4 hours of heavy use. With power management and the way people use things and turn on and off, we're hoping to stretch to an entire workday on one charge. That's the goal.
Are you looking at having a digitized pen interface? You mentioned tablet PC.
Digitized in terms of?
Instead of a touch-sensitive screen, an active pen-sensitive screen?
We've looked at some of the technologies. We don't really, right now, see a compelling reason to do that. It's, we've been able to get by with the touchscreen and run. We love, for instance, the handwriting recognition in Windows XP because it improved a lot. And it works very well with just our touchscreen right now. So while you could certainly do that, the question would be, would the advantages of doing that really work in a handheld? And it's not particularly clear that it would, because your actual resolution of your hand and touching a 4-inch diagonal space is not necessarily any worse than the resolution of a standard 3-wire touchscreen. In the back.
To comment on your form factor, did anybody mention to you that the product looked a lot like a Game Boy?
I'll let Ian handle that one.
Yeah, actually, we looked at the Game Boy as one of the models that we thought was a really well-designed device. And that's why actually, one of the things that moved us to using a force-sensitive joystick for the mouse buttons is that the generation below us has grown up on Game Boys, and so a two-handed interface is probably more natural to them than those of us who use PDAs doing a touchscreen, that this, to them, will always be natural. And that's very much why we went to this look.
How does that, do you think that's a benefit or a barrier from replacing any current product you have in the enterprise? Because, it's Game Boy, it's good for playing games. Not so good for
it's a perception barrier, certainly. I mean, when we learned some very interesting things taking this to the CeBIT trade show in Germany last month, and one of them was that nobody thought it was a Game Boy, but people really thought it was a pocket PC device because they refused to accept that you could have a laptop in this shape and this size. And similarly, so you run into a lot of perceptual problems like that are similar to confusion with a Game Boy, but I think anytime you're doing something that sort of breaks the paradigm of what people expect this much, those are the least of your problems.
Right. Game Boy being so personal, it's not really conducive for sharing. I would say that this product probably compares to that with the UPS kind of we use today. And somebody I don't know how to use it as
Well, it could certainly replace a lot of industrial handheld uses. I mean, one of our goals was, sure, if you're UPS, you can, if you look, they had their machine custom designed, and if you go visit a UPS office, they've got custom designed racks that they all rack into and network and update, and that's great if you're UPS. Well, our goal was to provide a product that if you're not UPS, that you could still deploy a handheld solution in an affordable way. Just one other point about the confusion of the interfaces. One of the things I thought was most interesting about showing this product in Europe was the different reaction you got to the keyboard. And this is an example of what people are used to and how they get used to interacting with machines. So in a similar way to the fact that people are used to Game Boys means that they immediately sort of get this idea of this stick. Well, in Europe, the penetration of the rim is a lot less. So Well, in the U.S., everyone picks it up and goes, "Oh, it's like the rim," and starts typing. Well, in Europe, people pick it up and they go, and then they put it down and they start going like this. And it was really very obvious that it was because we had to pick it up and show them, "No, type with your thumbs," and then they got it. But it was very obvious that their different experience with computing devices drove how they initially interacted with this one.
Is this as robust as the Game Boy? That would be my main criteria.
So one of the questions we get a lot is, how tough is it? Is it ruggedized? Can you drop it? And in the same way, like Ian mentioned before, you can't please everyone. We get some people when they say, "Well, can I pick it up over cement and drop it like this?" And we say, "Well, can you do that with your laptop?" And they always say no. It's tougher than a laptop, but I wouldn't want to put it up against it. I mean, the difference is mainly the hard disk, which we've shock mounted to the best of our ability, but it's not going to take the same number of Gs as a Game Boy is.
Okay. Game Boy's all right, because that will be fantastic if it were.
It's pretty tough. We have not, to date, broken one at all through impact, and we've dropped them and mangled them a fair bit. But that said, we haven't tried to drop them, do a drop test.
One of the things, a couple of things that were mentioned early on was research on mobile antenna design and front-end speed recognition. Is this something I would mind putting into this machine?
Yeah, this is blue sky stuff. So this is not what Tiqit is focused on. This is what we're pursuing as a parallel enterprise at Stanford with the idea that if we can actually get this to work, somebody might adopt this, one of these speech companies or antenna design companies might adopt this in a way that would integrate very nicely with the handheld space. And then we can incorporate some of these ideas into the device, both to improve the user interface on the speech side and to improve the quality of wireless communication on the antenna side. It's something that at the moment is definitely not anything we're going to be putting in this machine in the next 24 months.
There's the things that Vaughan studies, and then there's the things that we'll actually put on the unit. And the barrier between those is it, all right, it's very interesting and it's good research, but is it practical? And today. Yep. And the sort of, like I mentioned before, you have to take a step back. Well, the same way you take a step back in components, you have to take a step back in technologies. And while in a research way, you can prove that directionalized voice recognition and sound in and out works fine, it's not practical yet.
One of the strengths of the PC has always been its convertibility, the fact that you can get under the hood. I think I did some reading on this device, and the 10 gig drive that's in there is a fairly common footprint. How difficult would it be for me to get a 30 gig drive or something like that, put it in there, and then load an OS on it?
Well, right now,
I assume if I crack the case, I've voided the warranty.
right now, the disk drive that's in here is the highest density disk drive in that form factor that's available.
Oh, it is. Okay.
So
it's 10 gigs though, right?
It's 10 gigs, but it's not. So it's not an option right now. I think in mass production, you might try and make the disk drive fairly easily accessible.
Okay. And then what about the prospect of loading my own installation of the OS on it?
Right. Now, the easiest way to do that is to either hook up an external CD-ROM drive and just do it like you do on any computer, or one of the things that we put in the specification was the ability to boot from a PC card drive. Okay. So you can boot to that and then do whatever you want with the other drive. So while it's not like a PC in that it's not something you rip apart and swap parts out of, it's very much like a laptop in that we're not going to make any decision about what OS you run on it or how you use it.
Okay. So it has all the standard laptop pieces. It has a BIOS. It has something that I can understand that I get access drives with. And I would assume I'll be able to get drivers for your specific sound hardware or whatever from the website or whoever else is manufacturing it.
Yes. So the idea is that it supports all the things you expect a PC to do. And so some of the people who are really excited about it, which is not super productive in a business sense, is the Linux community. Because we get besieged because they could actually deploy Linux on handheld and not baby Linux or miniature Zorus type Linux, but real Linux. And that's why people get very excited about the possibilities.
This is going to become a major Quake box or anything. What kind of 3D processing and DirectX support do you see having?
That's one reason why we were evaluating the Transmeta processor, because right now we're using an integrated processor which includes video support, which means that it's a little bit on the slow side. So I wouldn't want to play Quake on this device. It will, and it's equivalent to a PC a few years ago. But one of the things we're looking at is, particularly with some of the advances in memory technology, is jumping to a real sort of high-end video chip that would just give us a better depth.
You guys have won.
Because it's a great game machine.
Does the screen general really don't
They don't have $1 billion going to spend.
So it doesn't support, at least the current version doesn't support anything other than mirroring, but it doesn't turn off. So if you change resolutions, you'll see a subset of the larger screen on here and then the full screen on the external, because the external one will support up to 1280 by 1024. And the goal there was that you could drive monitors or projectors.
That's one of those.
Just what the processor provides. They're fairly minimal in comparison with modern standards.
That is, how much of the time does your machine spend on cache circuit?
I don't have a good answer for that. It hasn't been an issue. We've had obviously so many other issues, but it's because we have so little control over it, we haven't particularly wanted to study it because we can't do anything about it. I can certainly give you more information separately if you're interested.